Assalamu alaikum. Good morning, everyone. My name is Associate Professor Dr. Norris Wadi Ismail, and today I will be presenting our research on the aerodynamic analysis of a dart paper airplane using ANSYS-CFX simulation. This study was conducted by myself, Hazim Sharuddin, Muhammad Hissam Basri, and Noura Fiza Jamiri from University Technology Mara. To begin with, paper planes, inspired by Japanese origami, serve as simple models for micro-air vehicles, also known as MAVs. Despite their simplicity, dart paper planes have been underexplored in terms of aerodynamic performance. Our objective in this study is to analyze the aerodynamic performance of dart paper planes using CFD simulations via ANSYS-CFX. There are several challenges we aim to address in this study. First, the aerodynamic performance of dart paper planes has been underestimated in previous research. There is a lack of comprehensive analysis using advanced CFD simulations. Understanding these aerodynamic characteristics is essential for MAV applications. Therefore, our goal is to validate and enhance the understanding of dart paper plane aerodynamics using ANSYS-CFX simulations compared to experimental data. Now, let's discuss our methodology. We utilized ANSYS-CFX for steady-state, incompressible flow simulation, employing Rand's equations with the shear stress transport, or SST, turbulence model. For design and simulation, we modeled the paper plane using SolidWorks. The geometrical and flow domain were set up in ANSYS Design Modeler, and meshing was done in CFX-Free with a hybrid mesh for detailed flow capture. Moving on to the experimental setup, we used the following specifications. The paper thickness was 0.2 millimeters, equivalent to A4 paper, with a span of 160 millimeters and a wing area of 20,000 square millimeters. The chord length was 250 millimeters, with a leading edge sweep angle of 75 degrees. The weight of the paper plane was approximately 5 grams, with an initial speed of 5 meters per second and an angle of attack, or AOA, of 5 degrees. The boundary conditions included an inlet velocity of 5 meters per second, zero pressure at the outlet, and symmetrical wall conditions. Next, let's look at the lift performance. The lift coefficient increases linearly with the angle of attack, until it reaches the stall angle, after which it decreases. The maximum percentage differences between our simulation and experimental results were as follows. Lift coefficient magnitude at 11.9%. Maximum lift coefficient at 29.5%, and stall angle at 24.2%. In the pre-stall region, from angle of attack 0 degree to 10 degree, lift coefficient increases significantly and our simulation closely matches the experimental results. In the stall region, beyond angle of attack 10 degree, lift coefficient decreases sharply, with a slight divergence between the simulation and experimental results. Now, let's discuss the drag performance. The drag coefficient trends increase with angle of attack. Notable percentage differences in drag coefficient magnitude were observed at different angle of attack ranges. 37.3% at angle of attack 0 degree to 10 degree, 9.9% at angle of attack 12 degree to 20 degree, and 0.3% at angle of attack 22 degree to 30 degree. In the low angle of attack region, from 0 degree to 10 degree, drag coefficient increases moderately, showing a higher deviation in drag coefficient magnitude between the simulation and experimental results. In the medium angle of attack region, from 12 degree to 20 degree, drag coefficient increases sharply with simulation results aligning closely with experimental data. In the high angle of attack region, from 22 degree to 30 degree, drag coefficient continues to increase, with minimal differences between simulation and experimental results. Finally, let's examine the aerodynamic efficiency. The lift-to-drag ratio, which is a measure of aerodynamic efficiency, increases at early angle of attack stages, less than 5 degree, and decreases at higher angle of attack stages, greater than 5 degree. Our simulation results showed higher lift-to-drag ratio compared to experimental results, with the experimental maximum lift-to-drag ratio being 4.7951 and the simulation maximum lift-to-drag ratio being 5.8377, a percentage difference of 33.2%. In the early angle of attack stages, from 1 degree to 5 degree, the lift-to-drag ratio increases significantly, showing similar trends in both simulation and experimental results. However, at higher angle of attack stages, the lift-to-drag ratio decreases due to increasing drag, with higher magnitudes observed in the simulation results compared to the experimental results. In conclusion, our study demonstrates good correlation between experimental and simulation results, validating the lift and drag performance of dark paper planes through CFD simulations. This indicates that dark paper planes exhibit efficient aerodynamic performance, making them suitable for MAV applications. Future work could involve further exploration of different paper plane designs and optimization of aerodynamic properties to enhance MAV applications.